Hello friends, welcome to EC Academy. In this lecture, let us understand the problems on star-delta transformation. Let us consider the first problem. Here, we need to find the current in 10 ohm resistor in the given network shown in figure 1 using star-delta transformation. This is figure 1 where we need to find the current flowing through 10 ohm resistor. So to solve this problem, we can use a star delta transformation. If you observe the figure, resistor 8 ohm and 4 ohm are in series, whose total resistance will be 12 ohm. Now this 12 ohm resistance are connected in the form of delta between A, C and H. Similarly, 13 ohm resistor is in series with 17 ohm resistor whose total resistance will be 30 ohm. So we will be having three 30 ohm resistors between G, D and E that will form a delta network. So we will be having three 12 ohm resistor which will form a delta between A, C and H and three 30 ohm resistor that will form a delta between E, D and G. Now this delta network is to be converted into star network between the points A, C and H, and the second delta network should be converted into a star network between E, D and G. Now let us convert this 12 ohm delta network into star network. So for that we can use the formula to convert from delta to star. So let us convert the first delta network into star network as 12 into 12 divided by 12 plus 12 plus 12. So if we simplify this, we will get 4 ohm. Now we have found the resistance of one branch in star network. Since all the resistance are same, we can use the same values for other two branches of star network. So all the three branches of star network will have 4 ohm resistance. Similarly, we can solve this second delta network and convert it to a star network. So we can write resistance to convert the second delta network into star network as 30 into 30 divided by 30 plus 30 plus 30. If we simplify this, we'll get 10 ohm. So we can use 10 ohm for the simplified star network in all the three branches. Now, if we simplify this network by converting these two delta connections into star connection, we'll get this circuit. So, we have retained this 34 ohm and 10 ohm as it is, and we have connected a star network which consists of 4 ohm resistance, and we have connected one more star network which consists of 10 ohm resistance. Now, these 4 ohm, 34 ohm and 10 ohm are in series, that will form 48 ohm resistance, and this 4 ohm, 10 ohm and 10 ohm are in series, that will form 24 ohm resistance. So if we simplify this network, we will get this network where we are having 4 ohm in series with 48 ohm and 24 ohm in parallel, which is series in 10 ohm resistance. Now we can apply parallel formula for these two, and we can write 48 ohm is parallel with 24 ohm, so which will give us 16 ohm. So we can replace these two resistors with a single resistance of 16 ohm. So we will get the network as shown in this figure. So here we will get three resistors are in series, 4 ohm, 16 ohm and 10 ohm. So if we apply series formula, we will get 30 ohm resistance. So we can say the total resistance of the network is equal to 30 ohm. We can find the total current flowing through the network as I is equal to V by R, which will be equal to 180 volt divided by 30 ohm. Therefore, total current I will be equal to V by R. So the voltage is 180 volts and the resistance is 30 ohm. So the current will be equal to 6 amperes. So in the question, they have asked us to find the current through 10 ohm resistance. Now, to find the current through 10 ohm resistors, if you observe this circuit, let us take the current flowing through the 10 ohm resistor as I1. So, here we can apply the current division formula and we can say the total resistance in other branch is 48 ohm and total resistance where the current I1 is flowing is 24 ohm. At that case, we can write the current through 10 ohm resistor is I1, which will be equal to resistance in other branch is 48 divided by sum of the resistance is 24 plus 48 and total current is 6 amperes. So we'll get the current I1 is equal to 4 ampere. So 4 ampere is the current flowing through 10 ohm resistor. Now let us consider second example. Here 6 equivalent resistors each of 4 ohm are connected as shown in figure 2. Find the equivalent resistance between any two corners. So between any two corners we need to find the equivalent resistance. In the first step, let us convert this star network into a delta network. Since all the resistance are same, if we find one value of delta branch, it will be same for all the branches of delta network. Therefore, we can say the delta equivalent resistance will be equal to 4 into 4 plus 4 into 4 plus 4 into 4 whole divided by 4 ohm. Therefore, the equivalent delta resistance for all the three branches will be equal to 12 ohm. So we can write the internal delta connection and for all the resistors we can write 12 ohm. Now, if we observe the network, this 4 ohm and 12 ohm are in parallel. Similar to that, these two are in parallel and these two resistances are in parallel. Therefore, we can apply parallel formula for resistors 4 ohm and 12 ohm. 4 ohm parallel with 12 ohm, you will get 3 ohm. So we can redraw the network as shown in this figure. So we'll get 3 ohm between A and B, 3 ohm between A and C, and 3 ohm between B and C. Now, to find the equivalent resistance between any two corners, let us take corner A and C. We need to find equivalent resistance between A and C. So, between A and C, there are two paths. One is from A to C, which is having 3 ohm resistance, and another way is from A to B, then B to C. At that case, these two resistances will be in series. So, the equivalent resistance between these two will be 6 ohm. Then 6 ohm will be parallel with 3 ohm. Therefore, the equivalent resistance between the corners A and C can be written as 6 ohm multiplied with 3 ohm divided by 6 ohm plus 3 ohm. So, which will be equal to 2 ohm. So, 2 ohm is the equivalent resistance between any two corner of the given network. Now let us consider the third problem where in the network shown in figure 3, the numbers represent the value of resistors in ohm. We need to find the resistance between the point A and B. So we need to find the equivalent resistance between point A and B. In this problem, if you observe, we are having an inner delta network. So this delta network should be converted into star network. Since the resistors are same, if you find an equivalent resistance for one branch, you can use the same value for other branch in star network. So the equivalent star resistance value can be written as Ry will be equal to 4 into 4 divided by 4 plus 4 plus 4. So this can be written as 1.33 ohm. So 1.33 ohm is the equivalent star network resistance for this inner delta connection. So we can redraw the network as shown in this figure. So here we are connecting 1.33 ohm resistor in star connection in series with the existing 6 ohm resistors. Now these two resistors are in series. So we can write an equivalent resistance as shown in this figure. Now this inner star network should be converted into the delta network. So we can use the formula R delta is equal to 8 into 7.33 ohm plus 8 into 7.33 ohm plus 8 into 7.33 ohm divided by 8 ohm. So the equivalent delta network will be having the resistance of 21.99 ohm. Since the resistance are same, we can write 21.99 ohm for all the three resistors in the delta network. So we can redraw the circuit in this way, where we are writing the inner delta resistor which is converted from this star network, which is having the value as 21.99 ohm for all the three resistors because the resistor values are same. Now this 8 ohm resistor is in parallel with 21.99 ohm. Similar to that, these two resistors are in parallel and these two resistors are in parallel. So we can apply parallel formula. Since the resistors are same, we can use the same value. So we can say 8 ohm is parallel with 21.99 ohm. So 8 ohm parallel with 21.99 ohm. So we'll get the value as 5.86 ohm. Now we can replace those parallel resistors with a single resistance of 5.86 ohm between each corner. We'll get this circuit in this form where 5.86 ohm resistor is connected between each corner. Now to find the equivalent resistance between A and B, we can use the same technique what we have used in the previous problem, where this resistor will be parallel with these two resistors which are in series between A and B. So we'll get the equivalent resistance between A and B as 5.86 ohm plus 5.86 ohm will be parallel with 5.86 ohm. The equivalent resistance between A and B will be 3.90 ohm. So 3.90 ohm is the equivalent resistance between the point A and B. Now let us consider problem 4. Here, using star delta transformation, we need to find the current flowing through the galvanometer G in the Wheatstone Bridge network, which is shown in figure. So we need to find current flowing between the point B and D where a galvanometer is connected. Now the resistance between point B and D is given as 50 ohm. Now we can consider this as a delta network. This delta resistance between A, B and D can be converted into star resistance. So you need to find the resistance RA, RB and RD. So we can use the formula which we have understood in our previous classes. To find the resistance RA, we can use the formula RAB multiplied with RDA divided by RAB plus RBD plus RDA. So that will be equal to 10 into 40 divided by 10 plus 40 plus 50. So the resistance RA is equal to 4 ohm. Similar to this, we can find RB, that will be equal to RAB multiplied with RBD divided by RAB plus RBD plus RDA. So which will be equal to 10 into 50 divided by 100. So the resistance RB will be equal to 5 ohm. In the same way, we can find RD, that is equal to RBD multiplied with RDA divided by RAB plus RBD plus RDA. So which will be equal to 50 into 40 divided by 100. So the resistance RD will be equal to 20 ohm. Now let us use these resistors in this equivalent star network and we'll redraw the network. So this is the redrawn circuit where we have replaced the delta network with a star network. Here the 5 ohm resistor is in series with 20 ohm resistor. So we can replace these two resistor with a single resistor of 25 ohm, and 20 ohm resistor is in series with 30 ohm resistor. So we can replace these two resistors with a single resistor 50 ohm resistors. Here if you can observe, along with this 20 volt supply, 2 ohm resistance is given. So this 2 ohm resistor should be connected in series with this 4 ohm resistor. So which will be the internal resistance of this power supply. This is the circuit after replacing these two resistors with a single resistor and these two resistors with a single resistor. And also we have redrawn a 2 ohm resistor here which is in series with 4 ohm resistor. Now we can apply parallel formula for these two which will be in series with 4 ohm and 2 ohm resistance. So the equivalent resistance will be equal to 2 ohm which is in series with 4 ohm which is in series with 25 ohm parallel with 50 ohm. So if we solve this, we will get the resistance as 22.67 ohm. So this is the equivalent resistance in the network which is along with the voltage 20 volt. So we can redraw the circuit as shown in this figure. Now we can find the current through the network as I is equal to V by R, which is 20 volt divided by 22.67 ohm. So the current I will be equal to 0.882 amperes. So this is the overall current that is flowing through the network. Now if you can observe, this current I is divided into I1 and I2. So we can find the current I1 and I2. So we can say the current I1 will be equal to resistor in other branch divided by sum of the resistances multiplied with the source current which is 0.882. So the current I1 will be equal to 0.588 amperes. Since I is equal to I1 plus I2, we can say I2 will be equal to I minus I1. So the value of I is 0.882 minus I1 is 0.588. Therefore, the current I2 will be equal to 0.294 amperes. Now, to find the current flowing through the galvanometer between point B and D, we need to find the potential difference between point B and D. So, to find the potential difference between B and D, let us apply KVL for this branch. So, we can say minus 5 ohm into I1 plus voltage between B and D plus 20 I2 will be equal to 0. So, if we apply KVL to the loop GBDG, we will get minus 5 I1 plus VBD plus 20I2 will be equal to 0. So here, if we substitute the values of I1 and I2, we can find the value of VBD. So we'll get VBD is equal to minus 2.94 volt. Now this negative sign indicates that point D is having a higher potential compared to point B. Therefore, the current through galvanometer Ig will be equal to voltage divided by resistance. The potential difference between VDB is minus 2.94 divided by the resistance is 50 ohm. Therefore, the current through the galvanometer will be equal to minus 0.0588 amperes. So this is about problems on star delta transformation. Hope you have understood the topic. Thank you.